Okay, welcome everyone to today's 1W-MINDS seminar. It's my great pleasure to have Markus Faulhuber from the University of Vienna as our speaker today. Markus got his PhD at the University of Vienna, then moved on to the NTNU in Trondheim, coming back to Vienna and then spending some time in Aachen now. And now, since October 2020, he is a project senior postdoc at his alma mater, University of Vienna. As for awards, I should mention that for his thesis, he received the DOC Award by the University of Vienna, the city of Vienna, and he has numerous invited talks about his topics, including one that I heard on his recent results that I think he will, that I find very exciting. So I'm very much looking forward to Markus' presentation today.
Okay, so thank you for the introduction. As you can see from the title, it's about some optimality of certain sampling results. And I mean, okay, I can see that some of you will be quite familiar with Gabor systems already, but usually people are not that acquainted with them. So I will give a short introduction from the classical sampling to Gabor systems. First, I also need to mention that this main result I'm presenting here is a joint work with Laurent Betermin, who got a position at the University of Lyon only this summer, a permanent position, and Stefan Steinerberger from the University of Washington at Seattle. And let me also provide the arXiv information of the work I'm going to discuss. So let me just point you here to the figures. So it's for me, it's a rather long article, and if you want to read it, it's actually built up in a way that you can find all the necessary results within the first 4 pages. And if that is fine for you, then you're already done with the article. If you want additional information and a rough idea, then the article is about 15 pages long. And only if you're interested in all the technical details, then you will have to go also through the rest of this article. Let me also mention, I mean, even though you need some advanced methods to formulate and maybe also understand the problem, that the basic problem is not very hard to formulate and understand. And also the techniques that are used don't really need much more than maybe calculus 1 or 2. Okay, but let's start from the classical sampling theorem and go all the way to time frequency analysis. And we will be talking about certain structured function systems which have already been studied by Dennis Gabor as early as 1946. So that was around the same time that Shannon worked on his theory of information. And the important point that Gabor mentions is that the theory of communication was based on 2 separate but kind of dual methods, namely the description of a signal as a function of time, and the other method is Fourier analysis. And he wanted to overcome this drawback that you have only a look at one or the other, and wanted to join this together. That also led to a series of papers which ended actually in the Nobel Prize in Physics in 1971 for his invention and development of the holographic method. The reason why he got the Nobel Prize that late is because for holography, you need a laser, and that has not been invented until I think the 1960s. Okay, so just to set the notation, because the Fourier transform has always different normalizations. So I'm using here this 2 pi in the exponent, and like that, it's a unitary operator, and we have Parseval's identity and the Bloch-Charel theorem. And the other operators which are essential in time frequency analysis are the time shift, which is just a translation operator, and the frequency shift, which is just a modulation. And we then combine them together to a time frequency shift, where I forgot here to write that this is lambda. And we also see that they do not commute in general. So there is a phase factor appearing, which can often be ignored, but actually for the technical details we are about to encounter, or the problems, just keep in mind that this phase factor is somehow preventing more general results than what I will present today. So the idea of Gabor was to use some window function to localize the content of the signal in time, and then to perform Fourier transforms like piece by piece. And as you can see, you also have some Parseval-like identity. It's called the orthogonality relation. So in particular, if we choose G1 equals G2, and to have it norm 1, then this factor will actually disappear. And if F1 equals F2, we see that the short time Fourier transform is an isometry from the Hilbert space on the real line, or on RD, to the Hilbert space L2 of twice the dimension. And maybe just why do we use this VG? Because it has been called voice transform, and this is why this letter V got stuck. And one thing I also want to briefly mention is this fundamental identity. So the idea is always we want to localize something in time, and at the same time we also want some localization information in the spectrum. And then we see, okay, if we localize F with the window G, this is the same as up to this phase factor, which we simply ignore, as localizing the spectrum with the Fourier transform of the window. In particular, if you choose, I mean, okay, it's not an L2 function, but this bracket here can also be interpreted in a distributional sense. If you pick G to be the constant 1 function, then you get the ordinary Fourier transform, and the Fourier transform of, in a distributional sense, of constant 1 is just the Dirac delta, and then this will actually here just result in evaluating the Fourier transform at any point omega. Okay, the classical sampling theorem, without any assumptions now on F, it just formal statement is, if you have a band-limited function, which means the support of the Fourier transform is in some compact interval. In this case, we pick -1/2 to 1/2. Then we can actually reconstruct the signal from its samples on the integers. And all we need to do is we need to use the sinc function here, which in my notation, sinc of t is sine of pi t over pi t. As a kind of a basis. And we can also write this as taking the inner products of the time-shifted sinc function. This is kind of dual to what we have for Fourier series. So for Fourier series, usually we have something on the torus, but we can identify the torus with an interval of, say, length 1, and we just shift it so that it is from -1/2 to 1/2. And then we can develop f into a Fourier series. But this is nothing else than taking the inner products with respect to modulated indicator functions of this interval and use these as building blocks, kind of. And the idea in Gabor analysis is now to somehow mix these two representations of f by dropping the assumption on the compact support. So the idea is, if your support is large, then you just cut it into pieces. And so this is this picture, what you see here. So you have here this constant function in blue, black, and red. I hope you can see it. And so each part is supported on an interval of length 1. And then you start to modulate your functions. So here you have an oscillation of 1. Here you have an oscillation of 2. And so for each piece, you develop it into Fourier series. Or you can do the same thing if the support of the Fourier transform is large, then you just cut this into pieces, and by this relation that the Fourier transform of the translation gives a modulation of the Fourier transform, you can also use the sinc function as a building block. And these are actually two Gabor systems which are coupled just by the Fourier transform. I mean, if f is in L2 of R, say, then f hat is also in L2 of R. And so instead, you could also write f hat here if you want. And then you just put a Fourier transform everywhere, and you will actually get back to this series representation. Okay, and then this last example before we come to formulating the results. So this is a so-called multi-component signal. What you can see here is a function which on a certain interval, like here, is a superposition of two plane waves, one with frequency 2 Hertz here, sorry, where's the 2? And one with frequency 4 Hertz, because we already have the 2 pi usually in the exponent. And then we have a plane wave with frequency 1, and then we have what is called a chirp. So the frequency is increasing over time. And on the left-hand side, so in this picture, you see the real part of the signal, and then you take the Fourier transform. I only plotted the absolute values, and then you can see, okay, there is something going on at 1 Hertz, which is this interval here. Then there is something going on around 2 Hertz and 4 Hertz, which is this interval here. And you can somehow see, okay, throughout the signal, there is also something between 1 and maybe up to 6, 7 Hertz. So this is this chirp, but you lose all the information about when these things happen. So what you can do is you can localize your function as is depicted here, and then take a local Fourier transform, and you see, okay, in this part, there is something going on at 1 Hertz, and the rest is pretty small. I mean, you see all these wobbles here, and you should not expect that it is getting any better, because recall that up to a phase factor, we have VGF is VG hat F hat. And so G is the box function. So G hat is the sinc function. And so you cannot expect that it gets any better than this. So the decay in frequency will be not very good. And if you do this now for each instant in time, you can build a two-dimensional representation of your one-dimensional signal, which will then look like this. Let me maybe zoom in a bit. Okay, so what you see is first you have this superposition of two plane waves with frequency 2 and 4. Then you have this wave with frequency 1, and after that you have this chirp. And so in this picture you see pretty clearly what is going on. And now let me just check if I can get back to original size. So, okay, that seems to work now. Maybe one smaller. Oops, sorry. Okay, and if you want a better localization in time and frequency at the same time, then you should probably not pick the box function, but maybe something like the Gaussian window. And so this is now the spectrogram on the left-hand side using the Gaussian. And you can see, or I hope you can see on your screen, here you have all these wobbles, which are like the artifacts of the sinc function. And clearly this is not the case here with the Gaussian. So you have a much clearer picture, kind of. And we started with sampling and we want to end with sampling. And so the question is, we don't want to use the whole information that we compute from this short time Fourier transform. We only want to know the function in this time frequency representation on a discrete set. And I mean, okay, if I already know the picture, then I would probably use a sampling pattern like on this left-hand side, because then I clearly cover all the important information. But I don't always want to adopt maybe my algorithms or whatever to the situation. And so the question was, is there some sampling pattern which gives stable reconstructions for any function in our Hilbert space? And the conjecture is then that this pattern, which you see here on the right, should actually be optimal. I will explain later or in a few minutes why this conjecture has been raised. Okay, so this has been a kind of introduction from sampling to Gabor systems. And what is a Gabor system? A Gaussian Gabor system. So we have our Gaussian function here in Rd. I mean, okay, we will restrict d to be equal to 1 actually for the rest of the talk. This here is just a normalizing factor. The thing is, it's Fourier invariant. And then we take the time frequency shift. So recall, this is a modulation by omega and a translation by x of phi. And we pick these time frequency shifts with respect to some discrete set lambda, which in the sequel I will always assume is a lattice. For the general theory, it's not necessary, but the results we obtain are only for lattices. And the goal is now to find such a representation, which is something like a mixture of this Fourier series, because you have the modulations in this time frequency shift, and this sampling theorem of Shannon, where you have the translations of the sinc functions, but your window G should be something nice, and we will always now pick the Gaussian window. Associated to such a Gabor system, we have a frame operator, and this formula here is should be compared to an orthonormal expansion of an element in a Hilbert space. But in general, this frame operator S lambda is not the identity operator, and so in general, this object here will not be F in general. But what we would like to have is instead of this, so this here is more or less the Bessel inequality we know from orthogonal systems. And if we also have a bound from below, we see that this middle expression, which could also be written as V phi F at lambda squared. So we sum the energy from the spectrogram, and we want it to be somehow equivalent to the energy of the original signal. And I have already written it here. So this is just the inner product of S lambda F with F. And so the best possible bounds, A lambda and B lambda, that we can get are actually the operator norm of S and the operator norm of the inverse. And the quantity we are then interested in is the condition number. What can we do if we know that this inverse operator is bounded, and then we can just apply it here. And then one can choose whether to pull it through to apply it to this phi here. This is one option, or the other option is you apply it here. And then you get a series representation of the kind that we seeked. And for numerical reconstruction and stuff like this, of course, it's always interesting to have a small condition number of such an operator. And that led to the conjecture of Strohmer and Beaver. Namely, they asked the question, which lattice is the best to minimize the condition number of the Gaussian Gabor frame operator. And so this paper is from 2003. Thomas actually mentioned the conjecture at an ESI workshop, I think, in 2001. So actually it's more than 20, or it has been more than 20 years old. And how did they come up with this? If you have a look at the frame inequality, instead of using V phi F absolute value squared for all F, you can just approximate your bounds by just having a look at V phi phi, or maybe a time frequency shifted one. And this is just another Gaussian. And since this Gaussian is somehow concentrated on disks, Thomas had the idea to use the theory of sphere packings. And so it is known that the best possible sphere packing or disk packing in 2 dimensions is given by the hexagonal lattice. And then this is how he came up with this conjecture. So maybe not all of you know what the lattice is. So let me just briefly recall this. So a lattice is mainly you take a basis of your Euclidean space Rd, and then you only take integer linear combinations. So in the end, what you get is a discrete co-compact subgroup of your Euclidean space, which could also be identified with a torus. And so we pick some matrix M. The columns of M are the basis of Rd, and then we just take integer combinations. And the co-volume, which is usually called the volume in the theory of sphere packings, is then the absolute value of the determinant of your matrix that you choose to describe your lattice. Okay, what you can probably already see is, since you take the absolute value, you could just pick some matrix with determinant 1 and then just use some scaling factor, which is then the volume of the lattice. So alpha in this case would be the volume. And so now it's a bit too big. What you see here is, actually it was fine. the square lattice on the left and the hexagonal lattice on the right. And it's called like this, what I have depicted here, for example. So this here is the so-called Voronoi cell of the lattice. So every side inside this regular hexagon region is closer to this lattice point in the middle than to any other lattice point. And this is where the name comes from. Sometimes it's called a triangular lattice because you always find equilateral triangles like this. It should not be confused with the honeycomb lattice, which would be something like this. But without this point in the middle. And this is not a lattice in the mathematical sense because it does not have a group structure anymore. Okay, but physicists usually still call it a lattice or chemists. But as a mathematician, I would say it's a periodic structure. So there have already been some investigations in this direction about minimizing the upper frame bound, like a couple of years before the work of Thomas and his student. And so, for example, this is found in Tolmieri and Orr, where they say a lengthy argument shows that B lambda is minimized by the square lattice among all rectangular lattices of even oversampling, so of even density. And actually, they refer to private communication with Janssen. And so in 2017, Stefan Steinerberger and myself could not only show that B lambda is minimized in this case, but also that A lambda is maximized in the case of even oversampling for among all rectangular lattices, only for the square lattice. In particular, this implies that the condition number is minimal in this case. What we also find in the article of Thomas and Scott is, so they say it's interesting to compare the condition number for these two lattices. So these two lattices are the square lattice of density 2. Sorry, I did not mention what density is, so I described what the volume is. The density is just 1 over the volume, so the average number of points per unit volume. And so in the first case, so this is for the square lattice, they find that the condition number is the square root of 2. And numerically, they observed that for the hexagonal lattice, it's suspiciously close to the cubic root of 2. And then they stated, we believe this is the minimal condition number achievable for density 2. So this is actually the conjecture they provide. They had some more numerical results which compared the square lattice and the hexagonal lattice, and the hexagonal lattice would always beat the square lattice. But the original conjecture was for density 2. But over the years, you know, it becomes folklore. A lot of people try, a lot of people do numerics, and then it seemed to hold for all densities. I will then explain you in a couple of minutes why I think, I also believe it's true, but it's actually a daring statement, I have to say. So in 2018, so 1 year after the work with Stefan, I could show that actually the upper frame bound is minimal only for the hexagonal lattice, again for even density. And the new result is that also the lower frame bound is maximized in this case. So as an implication, we see that the Strohmer and Beaver conjecture is indeed correct, at least for even oversampling rate. And here comes now the crucial part, why we can only do it for even oversampling. So, I mean, often people use some kind of Sachs transform methods or something. Janssen uses some duality theory. So instead of having a look at the frame operator, he had a look at the following operator. So he takes an operator from little L2 to little L2. And so he takes a coefficient sequence and builds a function in capital L2. And then he analyzes it again. And so you get a sequence again. And actually, I now wrote here always lambda, but actually it's the adjoint lattice. I will explain later what the adjoint lattice is, but you already see it down here. And there is a kind of duality theory. And what he could observe is that this operator from little l2 to little l2 can actually be represented by pi lambda prime of G with pi lambda of G. So lambda prime and lambda are just different points. And so just assume that the lattice is C2 now, so the integers. What he observed is that this bi-infinite matrix has a Laurent structure. So it's kind of a Toeplitz matrix, which means on the diagonals, it is constant. And then there is the theory about Toeplitz matrices and Laurent operators. If you have such an operator, then you can compute the spectral bounds by building a Fourier series where the coefficients are the entries from one diagonal. And the reason why this only works for even oversampling that well are these commutations relations, which I mentioned in the beginning, that modulation and translation do not commute. They produce some phase factors. And if you have integer oversampling, everything is actually fine. So also you will only have blocks of size 1. But this here will have a negative sign. And the negativity of the sign makes the computations much harder. Here you have +1. So you have alternating signs in your rows. And so you would have some alternating signs in here. And then you have a competition of minima and maxima, and that makes everything really, really tricky. And in general, if you have an oversampling rate of P over Q, no common divisors, then these blocks will be of size Q times Q because of this commutation relations. And so what you get is actually, you don't get a Fourier series, but you get a vector valued Fourier series, or a matrix valued actually. And then you need to determine the smallest and the largest eigenvalues. And then you need to optimize these eigenvalues. And the entries of the Q by Q matrix will be of this type. And so you will have polynomials of these series with different signs. And so you will have much more competing minima and maxima, and I don't want really to touch it. Maybe the case Q equals 2, but honestly, I think this result is already as good as one can at the moment go, maybe with the methods that we used. So I think it needs other ideas for other rational oversampling rates.
Could you shortly, Markus?
Yeah.
Markus, could you shortly comment on what sigma is in the exponent?
Oh, sorry. Yeah, of course. Sigma. Yeah. I would have done that in a moment, but I can do it now as well. So usually, so usually in a Fourier series, so usually this would be the dual lattice, and you would have the inner product between lambda in this dual lattice and C. But I want to use symplectic methods later on, which I will shortly explain. And the sigma is the standard symplectic form. And in short, it's, just taking like this. So you multiply it with a matrix J, and the matrix J is just a rotation. Okay, so it's more or less, so you can think of it as the inner product, but you mix the coordinates a bit differently. It results in the fact that you get a skew-symmetric form actually. But the reason why I want to use symplectic methods is explained in a couple of slides. Yeah, but thanks. Yeah. Okay, so what we see also is, okay, so we have some Gaussian here. We have more or less a Fourier series with Gaussian coefficients up to this strange mixing of our variables. And in principle, the whole problem can now be reduced to something which can be understood by any undergraduate student. So it boils down to Gaussian lattice sums. So what is a Gaussian lattice sum? So we only consider now a matrix of determinant 1, because we put this scaling factor alpha here, which takes care of going through the different volumes or densities or oversampling rates, whatever term you prefer. And so what you do is, okay, you take a Gaussian and you sample it on a lattice and you sum it. And then you shift the lattice. And this is just the Gaussian lattice sum. And now you can start to ask all kinds of questions. For example, which lattice maximizes the minimal value among all shifts? Or which lattice minimizes the maximal value among all shifts? And this is, of course, motivated that here we need to find the minimal value of this Fourier series and the maximal value of this Fourier series, and then we want to optimize with respect to the lattice. And the part that Laurent, Stefan, and I had to deal with was just this maximizing the minimal value, because the other part has already been done earlier. And sorry, I thought this slide is coming later, but it's coming apparently now. What we also need later is this Poisson summation formula. So if you take a function on a lattice and you shift it, this is the same as using the dual lattice, taking the Fourier transform of the function. And because translations become modulations, you have this modulation factor. And so you have a Fourier series associated to a periodization of your function. Okay, this is, I mean, it's a classical result. Just here's the definition of the dual lattice. And it turns out if you describe it in terms of a matrix, you just take the inverse matrix transposed. And as I said, I want to use symplectic methods. And symplectic methods only work in even dimensions, but we are in dimension 2, so everything is fine. And basically, as I said, we have this sigma of t and omega is just jt times omega, where j is again this standard symplectic matrix. Sometimes the minus sign is put on the other block, but it doesn't matter. You get the same group and everything. So you just replace the Euclidean inner product by the skew-symmetric inner product. You still have this Parseval identity. You still have invariance of the Gaussian. And what you also have is the Poisson summation formula, and you simply replace the dual lattice by the symplectic dual, which is called the adjoint lattice, and you have to replace the Fourier transform by the symplectic Fourier transform, and here you get again the standard symplectic form. And as you can see here, the condition is that this this skew-symmetric form only takes integer values. The difference is you just have to multiply your standard symplectic matrix on your dual lattice to get to the adjoint. But this is used in time frequency analysis because then time frequency shifts commute. This is the main motivation. So for Yeah, so you don't have any phase factor anymore, which you must expect in general. And this is why in time frequency analysis, it's more common to use the symplectic dual than the dual lattice. And okay, so I thought actually before that this slide would be coming, which we are now. So the result that we already had and why we don't need to deal with the upper frame bound is a result by Montgomery, already from 1988, who showed that if you don't shift at all, then the hexagonal lattice always minimizes this Gaussian lattice sum. And actually, that was only a minor adaptation I had to make for this article of showing that B lambda is minimized by the hexagonal lattice, is that this is also true if you seek to minimize the maximum among all shifts. And the result of Laurent, Stefan, and myself is then kind of the dual result to Montgomery's result, you know, only a couple of decades later. The tricky part is for the maximum, that is always attained in a lattice point. That is easily seen by taking the triangle inequality and using the Poisson summation formula. So maybe I can do the computation. Usually I should be able to do it. So this was by definition the sum over all lambda in lambda, e to the minus pi alpha absolute value of lambda plus c squared, which is by the Poisson summation formula. Doesn't matter which one. Let's take the classical version. The same as volume to the minus 1, sum over the adjoint lattice, e to the minus pi over alpha. Let's assume the volume is 1 because we have this factor. So then this factor goes in front. And then here you have absolute value squared. And here you have e to the 2 pi I lambda times c. So now you can take absolute values, take the triangle inequality. And so this complex exponential gets lost. And since we have a Gaussian which is positive, we don't need to write it. And so we have this inequality. And now using Poisson summation again, we get that this is this energy shifted by 0. Okay, so this is really easy. And so the maximum does not depend on any lattice parameters. And that is completely different for the minimum of this Gaussian lattice sum. In general, the minimum depends on the parameter alpha and on the geometry of the lattice, which is determined by 2 parameters in dimension 2. So we have 3 parameters which describe the minimum. The nice part is we have a result from Bernstein from 97, which says if you have this hexagonal lattice, then the minimum is attained exactly at the circumcenter of this equilateral triangle. If you take any general lattice, you can also build this triangle, but you see the minimum is clearly off from the point where the circumcenter is. And in general, it also, as I said, depends on alpha. And you can actually show, so in one limiting case, I never recall which one, alpha to 0 or infinity, it will always go into the circumcenter. And in the other direction, it will go to the midpoint of the longest side of this triangle. And it's also not clear to me how it wanders around, whether it walks on a straight line or not, I don't know. So this was a problem we did not really know how to deal with at the beginning. And okay, so here we have again this Poisson summation formula, which I already presented to you before. And the thing is now, if we have lattices in dimension 2, one can actually show that here this use of the dual symplectic dual is not necessary, and that we can actually plug in just a lattice. So this is also a simplification which was very nice, because we don't need to deal with different, with are we in the dual or not, we can always use the lattice. And what we then did is we took one part and the other part of the Poisson summation formula, and each and defined each as a theta function, similar to the classical Jacobi theta functions. And this gives this functional equation, which we also have for the classical Jacobi theta functions. And it allows us to reduce to the case where alpha is large. So by large, I always mean at least 1. And this is quite important, because if you have a look here, okay, you have this alpha in the exponent. If alpha is large, then it's basically only one term which dominates everything. But if alpha is small, then a lot of terms are of equal strength, and then everything becomes complicated. And so we could actually reduce the problem to the case when alpha is large, but therefore we needed to solve then 2 problems. And the next thing is you need to know a good parametrization of how you can actually explore which lattice is the best. And this is where the space of lattices comes in. So this is actually just, you know, the upper half plane, because this problem is invariant under rotation. So you can always somehow rotate your lattice such that the matrix is like this. And because we want determinant 1, we normalize it by y to the -1/2. So y should be positive. And so x plus I y with y positive is an element in this upper half plane. And then you identify R2 with C. And so you have 1 and tau. So 1 is the vector here. And then, for example, you have this point ρ2, which would be 1 tau. And now if you take all integer linear combinations, you get the hexagonal lattice. Instead, if you go to I, you get the square lattice. If you go to something further up, you get a rectangular lattice. And then there is this theory described in the textbook by Serre, where you have these linear fractional transforms acting on H, and then you find out, okay, there is a fundamental domain, namely this domain D, and that you can map, for example, this point here can just be mapped to this point by a matrix from the modular group, which is P SL2C, I write C2 now, which is just a special linear group with integer entries modulo plus minus the identity. And so if you pick a matrix from this group, this just means you pick a different basis for your lattice, but the lattice does not change. And so you only need to have a look at this domain D. And then what we actually showed is, okay, we took a slightly larger portion. We added this part here, and we could show that starting from any rectangular lattice, if you go to the right or to the left boundary, you will actually increase the value of the lower frame bound. And then we showed that close to the hexagonal lattice, there is an alpha region, so depending on this density. And in this alpha region, the hexagonal lattice is the unique maximum, and outside this region, there is no maximum. And this is how we showed that only the hexagonal lattice maximizes the lower frame bound. As I said, we did not know how to find the minimum, so we used a geometric simplification. Namely, we thought, okay, let's just try to evaluate in the circumcenter of such a triangle for any lattice. Okay, this is just, you can get some explicit formulas for this. I mean, I think you also learned it at high school. And the idea was, okay, can we now show that this point A, which is the circumcenter of this fundamental triangle, can we actually show that maybe this inequality already holds? Because we know that for the hexagonal lattice lambda 2, this is the minimum among all shifts. And what we observed is, okay, that's probably true, but we were not able to prove it. That was still too difficult for us to prove. And then in all these calculations, we found an algebraic simplifications. This is just the explicit formula for the Gaussian lattice sum. Maybe you don't want to read all of it, but it's just a quadratic form in K and L and shifted by A1 and A2. And then you can somehow split it. And the second part here is a classical Jacobi theta function. And what we observed is, okay, the coordinates A1 plus X, A2, they always fulfill this identity that they equal 1/2. So the dependence of A1 and A2 or of A at all gets lost in this second part. So we only have the dependence on A2. And computing the derivative, we saw, okay, this A2 is A2 prime. Take derivative with respect to X is always negative. And so that was somehow causing trouble. But we observed, okay, if this equals 0, then everything simplifies a lot. And then we were actually to prove that by constructing a point B, which coincides with the circumcenter on the right boundary line, but not for other lattices, and which also has this algebraic property. And in addition, so this B prime, so derivative with respect to X, so it's stationary with respect to X, then we could show that the minimum is only attained at the right boundary line for this point where we don't have a geometric interpretation for, but we constructed it in such a way that it's still the circumcenter for the hexagonal lattice, and so it's still the minimum in the hexagonal lattice. And so you have some point for each lattice which already has a lower energy than the minimum in the hexagonal case, and so in particular the minimum has to be smaller. So this is just a picture of the minimum here, this X, and this point here, which is not in the circumcenter, but which approaches the circumcenter as X goes to 1/2, is where we evaluate, and for some reason it worked out. So there is some stability result probably in the background, which we are not yet fully aware of. Okay, and maybe since we are already at close to the end of the time or over, I don't know, I will skip these details here. Okay. That is not really important. It's, as I said, calculus 1. I only want to come to an outlook. Is there something maybe for other window functions? Are there optimal lattices if we replace the Gaussian by something else? And the answer came quite so, well, it's not quite surprising, but the answer is sometimes. So this is ongoing work in progress with Irina Shavkulovska, who is a PhD student at our faculty at the moment. So I recommend that you follow her career closely. I expect that she has a bright future ahead. And so we took several different windows, mainly with exponential decay. And it turned out sometimes there is an optimal window, sometimes an optimal lattice, sometimes there is none. And sometimes the lattice for optimal lower and upper frame bond and condition number are different. Okay, and this is where I will end now. Okay, and time for questions. Thank you.